Well, welcome to Computational Conversations. I'm Jon McLoone, and today I'm going to be talking to Dr. Tom Wickham-Jones, who's the Director of Kernel Technology at Wolfram, about the Wolfram Compiler project. So, Tom, let's start by explaining to people what you've been doing at Wolfram. You're not a fresh hire.
No, I've been at Wolfram for a really long time. I've worked on all sorts of different parts of it, very much on the internals, the implementation of the Wolfram language. Originally, when I first came, I worked on the graphic system, though I've moved away from that. I've worked on things like Web Mathematica. I worked on integrating Wolfram into Eclipse, the thing we made called Wolfram Workbench. I worked on some of the early cloud things, but I've always worked a lot in the language, and I've been interested in implementation of computer languages. So one of the things I always worked on was compilation techniques, and for about the past maybe 7 years or so, I've been working on the Wolfram Compiler. So
I guess if not everyone knows about compiler technologies, what's the goal of the Wolfram Compiler project?
Right. So the goal of the Wolfram Compiler is to take Wolfram language code and convert it down to low-level machine instructions to get fast execution and to get a range of other benefits as well. So that's the idea of the compiler.
And so what kind of a performance difference does it make? How fast is faster?
Well, I mean, of course, as we know, when you ask me that, it sort of varies, but pretty typically for things running through the Wolfram evaluator, going to compiled code can run up to hundreds of times faster. If things are sort of you're running something that's already optimized and built in internal code, then sometimes there's no difference. So it really varies what you're doing.
I guess in my experience, I've been mostly doing kind of 1 and 2 line bits of code, nothing too involved, and I'm seeing sort of 5 to 10 times performance on fairly sort of simple kind of loops and operation, sort of arithmetic type operations. Is that typical, do you think?
That can be typical, but anytime you throw in like a little function, something that executes, which you might do for, you're using any true or sorting with a custom function, those are things where you get, huge performance benefits, bigger than 5 or 10. So,
okay. And how does it do it? Well, what's the methodology?
Right. So it uses, modern compiler technology. It uses an underlying technology that's very dominant at the moment called LLVM. That's very beneficial for implementing languages, and it goes through various sort of steps and things. It analyzes the Wolfram code, converts it into some intermediate form. It uses static type analysis to pick the right sort of code. It uses nice modern type uses a type parameterization system, so it generates special functions for lots. You don't have to write the same code, similar bits of the same code many times. You can write one bit of code and use it in many places. One benefit that it has is when it compiles things in the typical usage, it generates something that's optimized for your particular computer. Now, typically when we build one of our Wolfram offerings like Mathematica or something, we're compiling it for a generic machine whereas your machine might actually be higher spec than the generic machine. And so the compiler is generating code that's optimized literally for your hardware, which might have new instructions and things.
Does that change the way I actually write the compile code?
No, you don't do anything. We do all that for you. So that's some of the ways. And it's making use of lots of knowledge and things in research and things in compilers to optimize loops and eliminate dead code. And at certain levels, when you look at code in the right sort of way, you can gain a lot of reasoning and knowledge out of it, and then you can optimize it. So
for people who know the Wolfram language, they'll know that it's sort of natively not typed, that there's powerful pattern matching to control when a function should run, but you aren't actually typing the information. Is that an uncomfortable mix to try and bridge that gap between typed and non-typed in in the
Well,
compiler?
that's a good question. To write pure compiled code does require a bit more discipline, and the compiler step itself everything has to work. So in Wolfram code, you can sort of muddle through and you have a few problems in some places, but you can get some sort of essence of what you're trying to do. In the compiler, it's like all or nothing.
Right.
But if it works, it's probably going to do what you want. So there's a trade-off there. And to my way of thinking, it makes a nice complement that gives you the ability to optimize certain parts of core code or some, things like that. Maybe we'll talk a little bit later, but there's some interesting ways, I think, where the compiler offers opportunities for building like something like a JIT layer in the Wolfram language that I think would be really interesting. And I think its integration of a compiled language with an interpreted system in a very tight way, I think is pretty unique and something I find kind of
are you in
interesting.
the camp who believe that typed systems lead to kind of more reliable, not exactly provable, but more solid code?
Well,
Does it bring some of that sort of same benefit?
I don't think it's an all or nothing. I think, when I approach a problem, I often want to sort of free-formly prototype things, and I don't want to have to write lots of sort of stuff around it that can be quite complicated. So and there's kind of a nice workflow you can have with compiled code where you start out with interpreted code and then you start to add type annotations. The Wolfram Compiler has a very nice type inferencing system. So not for everything, but in many cases, you just add annotations on the inputs to your functions. Maybe you say what the output type is, and then everything else is sort of figured out. So you don't have to do a huge amount of stuff in the middle. But yes, it does add a sort of check or something. And I think I think there are times when you want that, and there's other times when it gets in the way. And I think it's nice to have that available for Wolfram programmers to take things to, if they want things to be very precise or exact, or if you really want to target, like special instructions on your machines or GPUs or something, you have no choice but to, do this type of thing. So I'm not sure if that's useful.
If you are reaping the benefits of typed code and compilation, what's the advantage over just writing it in C in the C++ in the first place, and then using the linking technologies that we have to link into the C code you've written?
Right, that's a fantastic question, and it's actually very beneficial to have a compiler that's so tightly integrated into the Wolfram system. And the reason is that it has knowledge of all these types and things, but some of the types that it has nice knowledge of is the internal types, the expression type of the compiler. So you get much tighter integration and you can pass things back and forth very easily and naturally between the compiled world and the regular Wolfram language code. And so you can really so sometimes some of the solutions that we make, so we have this like data structure library, and the data structures are a nice mix where really core things that are part of looking up things in a hash table or something are done in compiled code, but other aspects, maybe you want to print it out or get a visualization of the data structure, that can be done in interpreted code. So it really lets you delegate the style of code that's optimal, whether it's interpreted or compiled. And it's harder to do that in going totally to a sort of more alien code. And another big benefit is Wolfram language has a nice, concise, elegant structure where we can specify, lambda functions and pattern matching and things like that. And taking those concepts over into a compiled language that's tightly integrated is I think super interesting. So those are my benefits.
So
Yes.
the data structures, I guess I put those in a class of things where we're using the Wolfram compiler for our own benefits. Obviously, the principal thing, would you agree? The principal thing is you're trying to provide technology that our users can use directly.
Right.
But perhaps you should elaborate on the data structures and the other ways we're using
Yeah, sure, of course.
compiler for
Yes. So, in strongly typed compiled languages lend themselves very nicely to building classical data structures, things like extensible lists, mutable things like hash tables or, sets or hash sets or, all sorts of special types of things, bit vectors. So there's a thing called a bit vector, which is used in lots of our data processing functionality. So we started building up the library of these data structures very early on as nice uses of the compiler. And these were things that were hard to write in classical interpreted Wolfram code. And so the nice thing about those is that they're built and they exist and everything. So they're things that any user, you don't have to know anything about the compiler to benefit from them, but they're all pretty useful. And that's kind of a trend that we're trying to work on, is build packaged, encapsulated solutions built on top of the compiler that people see these as like new and different, and they're available. But John, you don't have to go and program up a disjoint set or something. It's all kind of done
For me,
for
it's
you.
all a bit like the way we treat automatic algorithm selection, that I'm not computer science trained, but
Right.
I'm capable of understanding the concept of some of these data types, but I would never sort of sit down and code them myself if I could help it.
Yeah, no, I think that, so it's a nice library that's nicely integrated that we built with it. Now we use the compiler in other ways. You were asking about that. So it's becoming more and more popular for developers at Wolfram Research, rather than using some of the other tools that they were using to start to use the compiler. Again, for the reasons it's nicely integrated and it's got a nice sort of ergonomics that fits in with the Wolfram language quite naturally.
Of course, a lot of the Wolfram language is written in Wolfram language, so there's presumably lots of
opportunities
to
for
go back and accelerate the
absolutely, yes. And so we do lots of things like that. Yes.
So people, if you've been using Wolfram for a long time, will probably be aware that there was a function called compile in version 2, maybe version 2.2, somewhere way back at the beginning. How does this compare or relate to that?
So yeah, no, it was version 2. The old compiler had some architectural differences. So it's based on top of a virtual machine that we put a lot of work into, and it was actually impressively fast, but it was still a virtual machine. So it had its own instructions, and it sat in a layer above the native instructions of the
so does that make
machine.
The new compiler much more portable in terms of the code
it makes
you don't need
faster? You don't have to have this sort of program that's basically interpreting a low-level instruction set. But it also, the old compiler had a lot of limitations in terms of extensibility. So it would have been hard to build something like the data structure library with the old compiler. So it was interesting, and we got some impressive results out of it, but it was kind of limited, and so we decided to sort of move on. And now there's a lot of knowledge and things in compilers that were a bit more abstract and a bit harder to reach in the old days. So that's where we got to.
So obviously it's an ongoing project. Things changing all the time. We just shipped version 14.3 as we're recording this a couple of weeks ago. What's the latest that has been?
Sure. So there's quite a lot of some nice new features in 14.3. So one area that we put a lot of work in over the past couple of years is trying to improve the ergonomics of the compiler. So but workflows, maybe that's a different term but the idea there is just to make it so that when you compile code and something goes wrong, you don't just get some unuseful message saying error, or it tries to show you things where you mark up where the code is, where the error that it got confused in the code that you've written. So that's an area we've been working on, and in the new version we also have some quite nice features for looking up, so you can search for definitions for functions and help find out what's what's supported and what's not supported, and the search for functionality and such like. Those are sorts of things that are pretty useful. They came from a lot of users internally of the compiler who were using it for things, and then they found this is like awkward to do, or how do I do this? And so we said, right, we'll go and fix that and make it all work for you. And that's actually not digressing too much, but another big advantage of having our own compiler rather than having, using some other language is, since we own it, it's like own it in the sense of it's ours. We are the main developers of this. It means we can make it very tailored for our way of working and make it very tailored for solving our problems, which isn't always the case with other technologies.
So you don't have to switch out of kind of idiomatic Wolfram styles.
Exactly. I like Wolfram styles. I think they're expressive and nice, and we want to support those. Anyway, going back to your original question of what's new in 14.3, we also have, we have a program where we steadily increase the range of functions that are supported natively in the compiler, and that's really important. We have a program, and maybe we could talk about that a little bit later, where we're trying to improve the speed of compilation. So the compiler produces very fast code, but the process to go from your Wolfram code to your compiled code, it's all written in the Wolfram language, but it's kind of slow. And so we have a program to try to improve the speed of that. And our current technique is to try to basically compile the compiler. So like eating our own dog food is the technical term for such a thing. So we've made, we try to make the compiler faster every version and cache, and etc. And maybe a last thing that I think is quite interesting, and this is the sort of thing that having a compiler gives you access to such things, is we have support for this new type of way of writing functions, and these are called incremental functions. And so these are functions where in a normal function, you enter the function, you calculate something, and then you return a result. And when you enter it, you create sort of internal state in the function and everything, and you return. So in the incremental functions, you write your code and everything, but you can exit from the middle of your function, and then a bit later you can return back into it. And so this is there's some nice examples in the documentation that show, and you can do lots of sort of quite innovative and interesting types of things with this, and it lends itself. You can consider this sometimes, because these are like frozen functions, so they can be a little bit like a model for multi-threaded. So you could have lots of these little functions, and you can sort of wake them up by calling them, sending them data, or extracting things out of them. And so that's pretty interesting, and that's a program we're going to start looking into, using this technology to have a program of things to generate incremental results. Because very often, if you're working on a problem, you might be, say, doing some problem in combinatorics, and in Wolfram language, there's lots of built-in functions for generating tuples and subsets and other things, but as we know from combinatorics, these things very often become
too big to return the whole result.
Very big to read. So returning partial results and operating on those is kind of interesting and beneficial.
And I guess in the natural Wolfram language, you would do that through global variables, but then you can't manage multiple instances.
It gets harder to, yeah, absolutely. It gets harder. So you can sort of do some of those things, but the compiler technology is kind of pretty state of the art and pretty nice. Now there's one last 14.3 feature that I must mention and that is something people have been asking for a lot, is a great big tutorial that people have been, when I give talks on it, I've had this in tutorial as a sort of internal tool that we used, and I put a lot of effort into cleaning it up, and it now ships standard with 14.3 3, and you can search for it and find it. And that's like a great big user manual. Now, these user manuals become more important now because of LLMs. So the documentation is a great source of examples and ideas and idioms. And so are, notebook assistant type LLM tools, which are really quite good and becoming, increasingly important, can use this documentation to give you assistance. So
And you're finding the LLM tools a good bridge for users to start using the compile? Does it?
It's not bad, actually. Now, obviously, we can get more and more in this, and we're just starting to really polish these. But I've used them to some quite good success. So yeah.
Well, finally, let's talk about the future. What's the vision going ahead to next version? You mentioned JIT. Perhaps we should start there.
Fine.
What's the vision?
So the thing that I would really like to do that really would be very beneficial to the Wolfram language is to, when you type in your untyped, your, unwashed Wolfram language program, to then have a little bit of analysis, maybe after it's run for a bit, and then to run the compiler speculatively on the program internally and then generate code that's advantageous.
There'd be zero input from the user.
There'd be no, it would just be like totally hidden from the user, except things would be running faster. Now, the impediment to doing that is, as I said, the compiler has to be much faster to generate.
But we have some
code.
technology for doing that kind of thing with things like plot and table, right? Already, if you're doing a plot of a numerical function, it does some compilation work.
Right.
This would step in and do that.
This would just be totally seamless. And so these functions, they have like options and things to select these, but you wouldn't have that. You would just write Wolfram language code, and it would, after a while, start to run. If you call something and you're always passing in a list of integers, it would go and create a special function that works for lists of integers for that function. So which would be super useful.
So what about is this a bridge into other technologies like CUDA? Is that on the roadmap of?
Absolutely. So the underlying technology LLVM that we base on is actually becoming very dominant in compiler technologies, and so we've and so all the when you do this like complicated CUDA programming to run things on your GPU, it's using LLVM based tools, and actually the same for other NVIDIA are very dominant, but they're not the only one, and many of the other technologies also use LLVM based tools. So we've put quite a bit of effort into integrate using the compiler to integrate with NVIDIA with CUDA
is this
technology.
Related to the new GPU array?
So the GPU array is one way to access into it, but this isn't in 14.3, but we're looking to have some really nice, smoothly integrated tools to execute code directly on, do programming directly on the GPU that I think is pretty exciting. And this is all very, very much based around the compiler, both GPU, both with NVIDIA and maybe some of these other like the AMD.
So I see GPU programming as quite a specialist expert activity at the moment. Do you think this is going to actually bridge the gap to make it something that anyone who?
I think it's certainly for me it's been very useful, because whenever I work in any language, I always want to work in the Wolfram language and then reach into that, just because I like the workflow of working in a notebook and saving things, and it makes working learning GPU code very accessible, and then you can make nice solutions that are integrated with with the Wolfram language. And of course you can use our notebook tools. You say, give me a CUDA kernel that does a certain thing, and then you can just execute it. That's kind of the goal that I'd like to get to. So, and I think these things are feasible. So yeah.
Well, it's a very exciting project. You say it's been going for some years now at this point. I guess it's got some years to run.
It'll run, keep us all busy for a long time. Yeah.
Great. And certainly rethinking, I guess, the very core of the Wolfram language. central to
I
what we do.
think we have to keep abreast of new ideas and all sorts of things, because the world's not a static thing. It's we've got to move along with it, and this is how we do it.
Well, I look forward to seeing that rolling out, and I think that probably covers that topic well enough for this week. So do come back soon for another computational conversation. Thank you very much.